Thank you everyone for joining us today for this installment of the Snowmass Early Career Big Questions in Particle Physics Colloquium. Thank you for being flexible with your schedules. We know that this is not the usual time for one of these, but I'm Christy Engel. I am a PhD candidate at the University of Maryland, and I'm privileged to be today's moderator. Just a reminder, if you have any questions for either of the speakers, there's a Google form where you can submit those. It's both in the chat for this Zoom call and in the general on the Snowmass Slack channel. We have today Chris Quigg from Fermilab and Jim Gates from Brown University. First up is Chris Quigg. He received his PhD at UC Berkeley in 1970. And after 4 years at Stony Brook, moved to Fermilab, where he has been ever since. He was head of the theory department there from 1977 to 1987. And his work on a lecture week, symmetry breaking and super collider physics charted the course for exploration at the Tevatron and the LHC. He was elected a fellow of the American Physical Society in 1983, and in 2011 won the J.J. Sakurai Prize for Theoretical Particle Physics with Estia Eichen, Ian Hinchliffe, and Kenneth Lane. We're very pleased to have him speak about the future of theory in particle physics. Chris, whenever you're ready, if you could share your slides.
Thank you. I'm trying to share my screen. And
excellent, we can see your screen.
Okay, very good. So thank you for the invitation. Thank you to everyone who has come or will watch on video. I'm very much looking forward to the conversation that will follow this, not only in the immediate future, but also offline later on. In some of the supplementary material that I put on the website, I posed 120 questions, specific questions about the future of particle physics. And it would be folly to try to do half of them or to do all of them twice as fast here. So I'm going to do something rather different. I'm going to begin by talking about some general strategies, general approaches to theoretical physics and the connection to particle physics in general. So about the first half of the talk will be taken up with these general questions. And then I'm going to selectively talk about areas of interest. And I will give less attention than I otherwise would to some topics that have been or will be covered in this series of lectures. My orientation, and part of the reason I stayed at Fermilab for such a long time, is to engage with experiment very closely. Lots of problems have walked through my door. And so I would encourage all of you who are budding experimentalists to walk through the doors of theorists. You'll be doing them a favor by asking questions that they don't know how to answer immediately and stimulating thought. Now, there are many different ways of doing science, many different ways of doing theory. Jim and I are, I wouldn't say at extremes, but we live in different neighborhoods of theoretical physics. More generally, in all of science and in particle physics, we can think about, at one extreme, the act of observation without controlling the circumstances. Then we have experiment, in which you try to control the circumstances under which you make measurements and observations. Theory that engages closely with experiment or observation, often called phenomenology, and formal theory, which may seem in the short run to be disconnected from the rest of observational science, but over the years has proved to be a very fertile source of inspiration for theory that engages with experiment, for experiment itself, and for observation. So all of these things are very closely linked. I tried to represent in a crude way here in 3 dimensions. So in fact, I have no idea what the shape of the space is or how many dimensions it has, but to show you some of the different ways that we think about doing science. So on the one extreme, there is the search for microscopic laws. That's often a fascination of people who do particle physics. On the other end from that, the fascination with phenomena clearly frequently preoccupies our colleagues who do nuclear physics or condensed matter physics. There is the notion of reduction, going to the smallest components, if you like, in a crude way, looking for new pieces of the Lagrangian of the universe. At the other extreme from that is the study of emergent phenomena, things that aren't manifestly obvious from the Lagrangian itself, but come about when you have a complicated system of many bodies, for example. There are those who take direct inspiration from natural phenomena and those who are governed by their imagination. Now, I think most good scientists occupy, at least from time to time, a large volume of this space, going in this way and that way. And I think that's an important thing, to not get stuck at one extreme forever and ever, but to look to the others. And so the question I would pose to you is, first, what is your home base? Where do you feel comfortable or most at ease? And then how far do you roam? Where do you go to look for new problems and to get inspiration for solving the problems that you find? In some of the discussions, you see references to a plan for 50 years. Or in the case of the FCC project at CERN, if you look at the schedule, it's a schedule that lasts for 70 years. Well, in one sense, that's very comforting to think that our future is secure for 70 years, if only we would do this or that. And I personally have great sympathy and enthusiasm for the FCC project. But it is a little bit scary to say that you lock yourself in with a plan for 70 years. And I invite you to think about how we would respond if one of our trusted colleagues, say Enrico Fermi, who could be more trusted than that, could he 70 years ago have anticipated what we're doing now and accurately given us the path that we should follow to get there? Clearly, in terms of the specifics of the investigations, the answer is no. Even in my short career as a particle physicist or as a scientist, the questions that we address today simply didn't exist when I was a boy. And so they manifestly didn't exist when Fermi was at the peak of his powers. Nevertheless, he did have a scheme which he put forward, not entirely in jest, and that was to build an accelerator fixed target, of course, at the time in 1954, reaching 5,000 TeV. It would be in orbit 100 miles above the Earth's surface, and it would cost a lot of money, $170 billion. Now, this is wrong on the specifics, or not completely accurate on the specifics, but the idea that one of the instruments that would be needed to go to much deeper levels of understanding would be a big new accelerator certainly has sustained us up until this time. By the way, when your colleagues or friends and family ask you, why are these things so big? Why do they cost so much? You can point out to them how much better we have done than Fermi's plan. At a fraction of the price, we reached an energy which is much larger and a luminosity which was unthought of in those days, even though we can't get to send all of our experimental friends 1,000 miles above us. So just a trivial remark is that if you make a program for several generations, it has to be flexible as well as visionary. And we have to take care that it not foreclose other promising initiatives. We have to be able to learn as we go and to evolve maybe the specifics, maybe the generalities of what we study. Certainly the scientific imperatives evolve and technology advances. And whatever we do must prepare us to take advantage of those developments. Okay, one metaphysical comment before we go on. It's something that I think is true about all of science, and in particular about physics and particle physics, but we don't jump up and down enough about it. And that is what I call the great lesson of 20th century science, the notion that the human scale of space and time is not privileged for understanding nature and may even be disadvantaged. This is true everywhere in science. Think of biology. You and I can, with our naked eyes, observe an individual ant or maybe a few of them. You don't know what an ant is until you study its DNA, going to a smaller scale, and you don't really know what an ant is until you've observed and studied an entire colony of them. So the idea that you have to go to smaller distances and larger, more expansive views, I think, is ubiquitous in all of science. In particle physics, we're privileged to have developed the renormalization group analysis that allows us tools that enable us to slide gracefully between low scales and high scales, short distances and long distances. And the notion of effective field theories, which helps us understand that we don't have to understand everything in order to make progress at a certain scale. We only need to identify and be able to make sense of the degrees of freedom that matter at a particular scale. So we change our resolution and extent in times and distances. Metaphorically, we have a need for diversity and scale diversity in the experiments that we undertake. So the final pontifical statement I'll make is that this discovery that the human scale is not preferred is as important as the discoveries that the human location is not privileged, which we can attribute to Copernicus, and that there is no preferred inertial frame, which we can attribute to Einstein and will prove as influential. And I think we scientists and physicists should take credit and joy in this sort of an insight and spread it to the rest of humanity. We talk about scales there. Scales are very useful for organizing knowledge. The scale that I show you on the left is actually taken from the security stripe of the 200 Swiss franc note issued just a couple of years ago, and which you can use at CERN to pay for a cup of coffee. You'll see that it describes the evolution of the universe from questionable times like the Planck epoch, inflationary epoch, quarks, electroweak, up to the present and beyond. We, of course, go even beyond the present with long lifetimes for things like double beta decay and long lifetimes for things we haven't discovered yet, like the instability of the proton. So scales are useful as a way of organizing our knowledge. They're also interesting and important as a way of setting targets for us. We're very lucky in recent history to have an understanding that the Higgs boson or something like it, something new on the TeV scale, would reveal to us important secrets about electroweak symmetry breaking. And that set for us the scale of energy and luminosity of the Large Hadron Collider and before of the superconducting supercollider project. We don't know where the next important scale is. We were quite lucky to stumble on that bit of knowledge from the past. We do know that higher energies will be needed to measure the triple Higgs coupling, to verify an important insight that the Higgs boson should regulate longitudinal W boson scattering. We have in mind conjectured scales like the unification scale at 10 to the 15th or 16th GeV, or the Planck scale about 10 to the 19th GeV. Both of those are out of direct reach. And so we lack for the moment the kind of target that we had in the case of the Large Hadron Collider. We have to try to set other targets for ourselves. So we can ask ourselves questions. At what scale are charged fermion masses set, or neutrino masses? Will there be new physics at the electroweak scale, 10 times, 100 times? People recently have devoted increasing attention to the notion that new phenomena might occur at macroscopic scales. So all of these things need to be kept in mind. And one of our colleagues said to me recently, one of our distinguished colleagues said to me recently that because we don't have the next scale in mind, we don't have a great calling, a great cause. And I think it's true that we don't have a specific target like the nature of electroweak symmetry breaking, but I would say that we still have the same cause that we have always had, which is to understand nature and to extend our understanding and learn the next set of questions to ask. So I do not despair. The same colleague asked me to remind all of us that the standard model did not always exist. I had the good fortune to exist before the standard model did, and to watch, and in some cases participate in its construction. It is a fabrication of human beings. It is very impressive, but it is fallible and it will not always exist in the way that it does now. So there's plenty of work to be done. And the fact that the standard model will change is an inspiration to us to work hard and to learn the ways in which it will change. Here is the most important question that I think we can ask ourselves. And that is, what do we know that is not true? It's very easy to get stuck in a particular way of thinking and to assume that because we've presumed that something is true for a long time, that it really must be true. But the question of what do we know that is not true, or for which evidence might be lacking, has often opened new avenues in physics. So one of the most famous, from my lifetime at least, if not lifetime as a physicist, is the notion of parity conservation, which is completely obvious that it should be true. But in the 1950s, people began to be inspired by experimental evidence and to question this, crystallized in a famous paper by Li and Yang. And then very quickly, by the famous experiments on cobalt-60 by C.S. Wu and collaborators, and by the coterminous coincident experiments by Garwin, Lederman, and Weinrich, in which they discovered parity violation in pi decay into mu, mu decay into electron. We had something that turned physics on its ear. People were stunned by this discovery that parity was not conserved in the charge current weak interactions. That inspired the V-A theory of weak interactions, that description, which, by the way, is responsible for the fact that we have to find a way for fermions, which couple left and right-handed components, to attain a mass if we want to have a gauge theory. The second of the discovery experiments by Garwin and company gives us the mechanism by which we measure G-2 of the muon today, and so has its own implications that go on. And the implications, of course, for the construction of the standard model are quite profound. The second, which has not yet had the same impact, but is an important one, is the observation, maybe a decade or so ago, by Arkani Hamed and Dimopoulos and Diwali, that we had little evidence that the 1 over r squared force law for gravity extended beyond essentially human scales, down to about the millimeter or centimeter scale. Well, we've not yet seen a break in this, but that is what governs the extrapolation to the Planck scale. And the mere observation that there wasn't a great deal of experimental evidence stimulated a new wave of experimental studies, which pushed the limits down an order of magnitude or so, and have given theorists new inspiration to take seriously the possibility that there might be additional dimensions of space-time. So that has been very pregnant, although it hasn't revolutionized the universe the way the discovery of parity violation did. So how do we progress? Well, I think it's very important to explore regions of the unknown and look for unanswered questions. And I learned from a French psychoanalyst who was not treating me that the job of a psychoanalyst is not to guess the secrets, but to try to guess where the secrets are hidden. So I take that as a good assignment for physicists and especially theorists. And finally, to seek out the soft spots in our current understanding, especially where the stories we tell are unprincipled, by which I mean not evil, but not founded on sound principles. So I give you a couple of examples of unprincipled theories that we sort of like and take seriously. One is supersymmetry, a great idea, beautiful idea, perhaps the most general symmetry we can think of. As soon as you invent it, you need to tack on R parity, you need to solve the mu problem to get the TV scale right, you need to obtain flavor-changing neutral currents, and so it's a hodgepodge at the moment, built on a beautiful idea. Similarly, Big Bang cosmology, based on the observation or the extrapolation that there must have been an early hot, dense period to the universe, requires inflation, requires dark matter, requires dark energy. That does not make these questionable theories, but it makes them incomplete theories, and we shouldn't simply repeat their names as if that's a talisman that will take us to knowledge. We really have to probe into them and understand why they're true, if true, because nature apparently has figured out how to solve all the problems that we need to solve in these two, and we need to take the cue from nature and figure that out. You can make similar arguments indeed about the standard model. It's a wonderful construction, but the particle content is something we take from experiment. The gauge symmetries we take from experiment. They don't appear to come from anywhere. Big Questions is the name of the series. I would simply point out that ever since Galileo, we have often solved big questions by posing and resolving small questions and weaving together the answers to those small questions into responses to big questions. Just before shortly before his death, I was corresponding with Steve Weinberg about conservation laws and symmetries, subject in which we both had an interest. Most theorists do, I think. And that caused me to look back at some of his old papers. And I found in this one some advice for young theorists and probably for young and old experimenters as well. So in 1965, he wrote a paper about something that was sort of preposterous to do, to look at quantum corrections to gravitational theory and to study the gravitational divergences in the infrared. He gives two reasons for attacking this problem that nobody cared about. One, because I can. So that's, I guess that's important to say because I can or because I think I can. And the second, very interesting, is to say because something might go wrong, and that would be interesting. Ultimately, nothing does go wrong in this case. But that's something that we can apply, for example, to what is the biggest discovery of all time, the discovery of the accelerated expansion of the universe, because it's a discovery of something that fills the universe, we think. The persons who carried that out thought they could do it. So that's because I can or because I think I can. I don't know whether they had in mind at the time because something might go wrong, but what they did is basically silly because you're measuring the deceleration parameter, and you should never bet against Einstein. Everybody knew the answer was going to turn out to be 2, except something did go wrong, and it was terribly important. So I think thinking of this possibility that not just because I can fill pages of calculations because I can, but because I will learn something from it, and maybe that something might go terribly wrong, is good advice. The last bit of advice is to learn about other approaches and other fields. Our theories, our understanding of electroweak symmetry breaking is tied to superconductivity. The old Ginzburg-Landau description directly inspires the Higgs mechanism. BCS theory is a motivation for technicolor, top color, things like that. Make it a habit of going to seminars. That's been very tough to do in person during the COVID era, but that's coming to an end. Learn from your colleague. The theorists mixed with experimenters, and for experimenters mixed with theorists. Torture each other. Okay, now for some specifics. One of the things that you hear theorists talk about very much is the hierarchy problem. This comes from things like the vacuum energy problem that in any interacting field theory, but in particular in something with a non-zero vacuum expectation value for the Higgs field, you get too much energy in the vacuum, too big a cosmological constant. We all learn that there's a quadratic sensitivity of the Higgs mass to quantum corrections. We've heard that there's something not quite desirable about elementary scalars. And there's a deep idea that small masses arise from symmetries that become exact symmetries. Now, lots of people refer to the hierarchy problem, but I think many fewer people actually think about it day by day. And I encourage thinking about it day by day, rather than simply repeating the old words. I think we were probably hypnotized by the fact that we had long ago posited 2 once and done solutions to the hierarchy problem, supersymmetry and technicolor, either of which would have been an invention on the TV scale that solved the problem forever. And I think we probably got carried away with the notion that our generation could be the one that solved these problems forever and ever. So keep thinking. That's the advice of some of the people who invented this problem for us. Okay, now I want to talk very quickly about a number of areas in physics that are open for us and should stimulate our thought. One is QCD is often left behind because it's the way we calculate backgrounds and maybe signals. There has been stupendous progress in the last years in both perturbative QCD calculations and non-perturbative or lattice calculations. Back in 1984, when we first started talking about grand accelerators like the LHC and SSE, it seemed very difficult that we would ever be able to calculate 2 gluons going to 4 gluons. Now at tree level, people simply write down the answer up to an arbitrary number of gluons, or at least a large part of the answer. And I have colleagues who do, I think, these for-loop diagrams before breakfast. So it's really quite impressive. The progress has been made. A little bit removed from the experimental applications have been brilliant work done on the nature of amplitudes, how we understand the cancellations among different amplitudes and so on. That is clearly going to lead us to new insights about the nature of field theory and about nature in the near future. On the non-perturbative side, we get to make these wonderful pictures of the action density in non-perturbative QCD to calculate things about the hadron spectrum, the phase diagram of QCD as studied in heavy ion physics and so on. And I think this is a wonderful theory. It's very complete and rich. And there are many, many problems that we could be asking and answering about it. One that I like is looking in soft particle production and high energy collisions for new production mechanisms. I think that's a place where machine learning to inspect the configurations might be very important. I also think that I've been interested myself in new body plans for hadrons going beyond the quark, antiquark, and 3 quarks. The techniques of resummation and a proof of confinement is still lacking. So if somebody wants to do that, and there is the strong CP problem, the one defect or incompleteness in QCD that may lead us to something very, very important indeed. A few words about flavor. I don't think you've had any presentations about that. Lots of the parameters of the standard model have to do with flavor, quark masses, mixings, same for leptons, CP violating phases, and so on. We have this picture of left-handed and right-handed quarks. They're different, and leptons, they're different, left-handed and right-handed. That's the parity violation discovered in 1957, 58. We don't quite know what the right-handed neutrinos might be. These patterns look the same. You sort of see the quarks and leptons and you're urged to put them together. So there are many, many things to study there. What is the connection between quarks and leptons? Is this the whole story? Are there more fundamental constituents? What about unitarity of the mixing matrices, non-universality, quark, charge lepton flavor violation, and so on? What is the effective violation? One of the things that haunts me is why we've seen no sign of flavor changing neutral currents, because any extrapolation of the standard model gives us flavor changing neutral currents. I want to say a few words about unified theories. It hasn't been a very hot topic of late, but it's there. We have the strong suggestion that we might be able to make a theory that would actually predict for us the weak mixing parameter sine squared theta by embedding the standard model gauge group in something bigger and studying the evolution of it. There are phenomena such as neutron anti-neutron oscillations, proton decay, and so on. New transitions between quarks and leptons to be studied. The idea that the evolution of the 3 coupling constants here, I plotted 1 over the couplings, is governed by the spectrum, has been taken as a way of maybe justifying the existence of new families of particles, say, for example, superpartners at TeV scale or so on. It would be wonderful if we could find ways to probe that directly. Just a few words about astroparticle physics, which you're going to be hearing about in the next presentation in these series. We don't know what the universe at large is made of. We have strong suggestions for subliminal on matter that we don't feel, the dark matter. We don't know the complete thermal history of the universe. We don't know why matter dominates over antimatter. We don't know what started inflation, if it happened, and we don't know why the acceleration of the expansion of the universe is accelerating. So the cosmos gives us a way of testing our theories, but also gives us stimulating questions about our theories. So as in paleontology, we need to learn to read new strata of the history of the universe, as well as in refining precision and learning how to use gravitational radiation. I'll say just a little bit about neutrino physics, in which there are many topics that have to do with not the big accelerator experiments that are so important for Fermilab's future and for the future elsewhere in the world. Tritium beta decay, neutrinoless double beta decay sources, things that rely on natural sources, neutrinos coming from out there. The challenge of detecting the cosmic neutrino background, they're all around us, 56 of every species at every cubic centimeter. How do we use the spectrum, the flavor mix of neutrinos arriving from out there to say important things about the sources and so on? It's a very rich theory. In that context, and as an example Snowmass problem, to which I don't know the answer, I think it's very interesting to think about a neutrino factory, not as something we do immediately. Maybe it's a second act for our long baseline neutrino experiments, but there's also an opportunity to make contact with people who have done femtoscopy programs or outlined them in electron scattering, and to see whether the amazing experiments we could do using 10 to the 20th neutrinos per year, using thin targets, polarized targets, active targets, could help us learn something about the nature of the nucleon and other important questions. There's one paper of about 20 years ago that you can click on here to see. Well, I think it's the last serious work that's been done. It's a fun problem of the kind that you could do at Snowmass. It's not advocacy for the moment, but just learning about possibilities. I call your attention to the tabletop experiments that are giving us important information about limits on electric dipole moments, magnetic anomaly of the electron and positron, magnetic moments of the proton and antiproton, now shown to be equal to an astonishing level, and charge to mass ratio and so on. Final Snowmass explanation is the last 2 years have been tough for everyone, young and old. Tell your colleagues what you need. Everyone's career and life has been impacted by this. And one of the things that I would hope, especially from young people at Snowmass, is what your more senior colleagues can do to make your life better and your scientific career more productive. So with that, I'll stop, and I'd be happy to take any questions or comments.
Thank you so much, Chris. That was excellent. Just a brief reminder of the format. We will have 5 minutes approximately for questions just for Chris, and then we will follow with our next talk from Jim Gates. And after that, we'll have 5 minutes for questions for Jim, and then we will have a discussion amongst all of us. So if you do have a question and you don't think of it yet, or we don't get to it, please feel free to still submit it. We can come back to it after Jim's talk. It was, I believe, Tejinder. I apologize if I'm not pronouncing that correctly. You had a...
Yeah, thank you. Thanks, Chris. My name is Tejinder Singh. I work at the Tata Institute of Fundamental Research in Mumbai. I'd sent you my papers a few days back, and I think I have something very important to say, namely that in particle physics, we have missed out on a foundational issue. What is the structure of space-time, even at low energies, in quantum theory? One can argue that you cannot label space-time by just 4 real numbers, because the quantum systems are obeying position superposition, and that induces space-time points to be also superposed. So if we instead replace the 4-dimensional space-time labeled by 4 real numbers and label them instead by non-commuting numbers such as octonions, then the symmetry groups of the octonions like E6 automatically dictate and show evidence for standard model symmetries, including the Lorentz group. And what is more, the geometry of octonions seems to dictate the values of the 26 free parameters of the standard model. In particular, I derived the low energy fine structure constant 1 by 137 and mass ratios of charged fermions. I think this is an important development and what you call the soft spot. So this is a soft spot, not realizing that space-time is non-trivial even at low energies, even when gravity is weak in quantum theory.
Okay, thank you for that comment.
Would you say something, please?
I think I'd like to hear more questions instead.
Okay, thank you, thank you, thank you, thank you.
Okay, are there any more questions from the audience specifically for Chris?
I think there's one in the Google form.
Oh, there is. It says, Chris, you mentioned some baryon number violation channels. What most excites you about these, and do you see a path forward for the funding of these experiments? And what is the best defense of the need for these experiments in your estimation?
So that's a big question. Well, the obvious place that you look is in proton decay. And that has a glorious history because when the first experiments failed to find proton decay, they invented a new form of neutrino physics that has been incredibly productive for us. So, you know, that proton decay, neutron eddy, neutron oscillations, things like that are the obvious direct observations. There can be leptoquark states discovered at colliders and so on. I think, you know, this is speculative, but it's a beautiful and profound idea. We need to have some way of breaking baryon number if we're ever to explain the matter-antimatter asymmetry in the universe. So I think this just comes as part of the general program we would make. Today, given what we have learned about the presence of these searches in colliders and in big detectors for neutrinos, I think the plea for funding comes as part of these general programs. It's a thing that you can do in the course of doing these other things, and that it is an additional motivation. So.
Thank you so much. Don't see any other questions. Unless there are anyone who has something that would like to raise their hand. But if not, we can move on to Jim, and any remaining questions can be saved for the discussion period afterwards. So thank you so much, Chris.
I will stop sharing.
Yes, thank you so much. Our next speaker is Jim Gates. He received his PhD from MIT in 1977. He was a University of Maryland Board of Regents professor with the Center for Fundamental Physics up until about 2017. He's been featured on several NOVA PBS programs, most notably The Elegant Universe. He received the National Medal of Science in 2013, becoming the first African-American theoretical physicist so recognized. Also in 2013, he was awarded the National Medal of Science by President Obama, and this is the highest recognition given by the US to scientists. He was recognized as a Black History Month 2017 honoree by the Mathematically Gifted and Black Foundation, and is currently the Brown Theoretical Physics Center Director, and began his term as the American Physical Society President in 2021. And we're very pleased to have him here to speak for us. So Jim, whenever you're ready, go ahead and share your screen.
Thank you. I'm sorry, can you still hear me?
Yes, we can.
Okay, great. Sorry about that sound problem. Okay, so first of all, I'd like to thank you and all of the organizers for having me here to give this talk. I was really reticent about this because I believe that people who have a fixed expertise should stay in their lane. And as the last time I seriously thought about phenomenology, I was still a graduate student. I was therefore a bit shy about coming to talk to some of the true masters, such as Chris. I saw Dave Hittman's name on the message and a few other luminaries. But in the end, you convinced me that I might have something useful to say. And so I'd like to go ahead and make my presentation. So I also want to thank Chris for allowing me to see his deck before I actually finished mine. And it had a major influence. So I want to make sure that everyone understands that I acknowledge that debt to Chris. So let's get started. Big questions. You'll notice I begin by showing the image of the Roman goddess, Janus, looking both forward and backward, looking forward with a face for a bright future, perhaps, looking backwards with perhaps some darkening for the knowledge of what has occurred. But of course, the paradox is that that knowledge is in fact the foundation for the future. There we go. So as I said, Chris shared his slide deck with me, and I was immediately struck by that. And as he mentioned in the talk, although I'm not completely diametrically opposite to him, to a large degree, my career has been not focused on phenomenology. Although the first two scientific papers I ever wrote were actually about weak interaction phenomenology. So if you put me in the corner where formal theory goes, instead of Chris's nice Cartesian axes, I would tell you theory looks like this to me. And of course, that means what exactly is going on here. So in order to talk in a way that I think it might add value to this group, I'd like to do a little bit of reminiscing, things that I've watched from the time that I was a graduate student. And as I said, started out as a weak interaction phenomenologist and therefore have always had a high regard for what goes on in particle phenomenology, as well as trying to make sure that I can keep abreast of major trends to the best of my ability. So that's the Janus looking backwards part of me. So what happened since the time I was a graduate student? Well, lots of dreams were fulfilled. The standard model came into existence. As Chris mentioned in his talk, it did not always exist. And in fact, I was also a student as its formulation was undertaken. So we have these nice charts that we can even see in high schools these days that take their place alongside of Mendeleev's table of elements. In the late 60s, particle physicists suddenly learned that they had to understand group theory. So this is a representation of the quark and antiquark triplets that are very well known. These are the octets, and then the decuplet. As those of you know, many of you on this session know that this one played a very special role with regard to Murray Gell-Mann's assertion of the importance of group theory, actually predicting the discovery of the omega minus before it was actually found on the basis of this chart, Archer. We've seen a dream machine build, actually two of them, the Atlas detector at the LHC, as well as the CMS detector there. These machines are so fantastical that I understand that they were the inspiration for a science fiction movie by the title of Angels and Demons, I believe, because the authors didn't really know that humanity had such technology. If we could go to the border, we might have Superman's vision to go underground and enter the LHC tunnel. And there, as we fly along, we see billions, over 100 billion protons in a bunch. Now in this cartoon, we only see 3 or 4, but as I don't want to have my screen completely pink, I've chosen to illustrate these as representatives. They travel around at 0.99999 point speed of light, and at the crossover points, they are allowed to collide with each other. This is a cartoon representation of the CMS detector. And of course, we can think about this as a fancy smartphone camera, and it takes pictures of these collisions with the hope that we'll see interesting things going on. And in particular, we have, since 2012, Higgs bosons have been created due to a process called gluon fusion. This is the Feynman diagram. We actually create the Higgs boson by having gluons fuse, put a top quark loop in the middle, and that couples to the Higgs bosons, which subsequently decay, and then we can detect them either in pairs of gamma channels or pairs of gammas, or in a 4-lepton channel with Z intermediate daughters from the Higgs boson before they decay into pairs of leptons. So we've got this wonderful chart that we can put in high schools these days. That happened all during my lifetime watching phenomenology with the Higgs boson added in 2012. I like to remind people that the announcement was actually on the 4th of July. So the Higgs boson in some sense was born on the 4th of July. In answer to the question that started really back in the late 60s, middle 60s or early 50s, late 50s with, excuse me, with the question of how could you have massive carriers, spin-1 carriers of forces. Shelley Glashow did some of the earliest work in this subject, and actually his work was the first place where the mixing angle between the neutral vector bosons was predicted. Well, there's a lot of other places that during my lifetime I've seen inspiration for particle phenomenology. We've decided to look up, and in particular, there's what some people call the cosmic collider, namely our entire universe, which is able to achieve energies far, far greater than the one that was shown in Chris's slide about a Earth circling tunnel that could be used to collide particles. We now know from our observations of matter and the standard of what's called lambda CDM, cosmological constant cold dark matter model that Chris alluded to, that the universe seems to be an exceedingly strange place where only a small portion, 4% or so, is really what we know in our science. And the other remaining large sector, dark matter next largest, we know typically from gravitational effects. And finally, dark energy because of the acceleration of the universe. And the latter two constitute 95% of what seems to be out there. We know from Einstein's theory of general relativity that the universe appears to have started with some sort of singularity. Therefore, as Chris alluded to in his talk, there must have been a phase when it was very hot and dense. Actually, if you look at Einstein's equations, there are 5 possibilities that the equations predict. And for a long time, we thought we were in the lambda equals 0, that is cosmologically equals 0. But 20 years ago, the acceleration of the universe changed our mind about that, as it is the simplest explanation for the accelerating universe we currently observe. We also have out there the cosmic microwave background, and that also provides us with more information on the structure of our universe, and we believe also its fundamental laws. The cosmic microwave background, of course, owes this discovery back to the 60s, to Bell Labs and the Holmdel horn, as it was called, that you see up there at the top, where the microwave emissions were first detected. Until today, actually, this is not quite today. This is the Planck satellite, which we're still using to observe the inhomogeneities of the cosmic microwave background to infer the fundamental laws. So cosmology has made a tremendous leap in terms of predictive theory, and it's typically around the 10% accurate to within 10%, which is amazing when I compare it over my lifetime. So we can look up and think about particle physics. And I tell young people that, you know, if I were young, I would seriously think about not doing particle physics, straight particle physics, but think about combining it with astroparticle cosmology type subjects. We have LIGO out there, which once again is probing these fundamental laws. And recently, the observation of the kilonova coalescence actually allowed a verification for, first of all, 3 active sites, but a verification of something that David Schramm and collaborators had predicted in the 60s regarding the production of the element gold. So we can see particle and nuclear physics by looking up. And then, of course, most recently, we have the Event Horizon actually imaging black holes. And from these images in the future, it is hoped that we will actually be able to observe the accretion disk around black holes, and therefore once again have a new probe into the structure of fundamental particles. Neutrino physics was mentioned in Chris's talk, and of course, my favorite neutrino experiment is actually IceCube, because it's just so unbelievable that you could actually, that we as a species could construct such devices in such harsh domains and actually use them to as our eyes on the universe. Of course, there's at Fermilab, we have Mini-Boom hosted. A large fraction of the community works on Mini-Boom. Seem to be thinking of the old accelerators. I'm going to come back and talk about something that started with Babar some time ago out of Stanford. And now we have a collaboration between Fermilab and Stanford in the Dune experiment, where the deep underground laboratory is actually used as a way to explore the science of the interactions of neutrinos. And something that warms my heart was the announcement in 2021 that the anomaly in the value of G-2 for the muon seems to be sustaining its life. People suspected this back in the time when Babar was active, and that's why I wanted to bring that part into the story of neutrino physics. So those are dreams fulfilled. What about dreams that were not fulfilled? Well, I don't have to tell you that the biggest one was the idea that supersymmetry was right around the corner. This is a sort of a dated schema showing the number of experiments looking at the various channels at the LHC for evidence of decades of superpartners or superpartners themselves. We can, first I showed the Atlas results, here the CMS results, all from around the same time, just short of a decade ago, and all were completely negative. I'd like to remind people that what's mostly being tested in the current round of experiments at the LHC is not really looking in the entirety of the parameter space of supersymmetrical extensions of the standard model. In fact, what is really being tested is something called the constrained minimal supersymmetric model, where sets of parameters based on various arguments that appear reasonable are chosen, and then those are used to create the templates that one might use to detect supersymmetric phenomena. I don't have to tell this group, but it's largely not understood by the public that we are in an era of science where it is not like going on a safari. You know, if you go on a safari, you pay a bunch of money, you go to someplace you've never been, and you can look out a window or maybe out hiking, and you'll say, gee, there's an animal I've never seen before. That's not how it works for us. It's not how it works for LIGO. We actually have to create templates and then ask our observational colleagues, do you see the patterns that our templates actually form? And so the templates that are being tested currently on supersymmetry are the ones mostly associated with the constrained supersymmetric standard model. However, although many of my colleagues were shocked that supersymmetry evidence was not found at the LHC, I was not among them. In fact, in 2006, I wrote this article, which appeared in Physics Today. The title of the article, as you can see, is String Theory Phenomenologically Viable? Perhaps this reflects my early roots in phenomenology, the fact that I would raise this question at that point in time and become seriously concerned. Because if you look at back, for example, back at the history of Snowmass activities around that time, a large number of them were devoted to trying to nail down the signals that we would be seeing that would work, that would indicate the presence of supersymmetry. And I'm sure that Chris himself remembers that work and during that time and the excitement that drove the community. I was concerned, however, because I had watched the field of supersymmetry from its birth, at least here in the United States. In 1977, I wrote MIT's first thesis on supersymmetry, having transitioned from weak interaction phenomenology to supersymmetry as basically as my professional love. So in this paper, I pointed out that, there's something very strange about the discussion, at least I thought very strange about discussions, and that is that though they were mathematically consistent, they were not principled using this the word in the sense that Chris was describing in terms of the mass scales. In fact, I could see no reason to expect the mass scales to be light. And I said as much in this article. Some things that I commend to people's attention is, one of the quotes is that if we use the masses of the neutron and the W as benchmarks, we can, crudely speaking, form the equivalent for particle physics for Moore's law. And it turns out that using that, you say, well, humanity progresses at a rate of about 1.5 GB over c squared per year in our ability to create new heavy particles. And given what I was worried about in terms of the arguments about the scales, I thought that it's just as likely that superpartners would be 30 TeV. Now remember, I'm a formal theorist, so a factor of 2 doesn't bother me. Maybe they're as high as 60 TeV. But the point is, I didn't see why. I didn't see an argument that I found convincing. And I'll return to that later when we get to talk about naturalness. And so on the basis of this, I became extraordinarily concerned that supersymmetry, because it was so widely accepted and discussed, that it might be an impediment for our field. And furthermore, I asserted that the first signals I expected to see from supersymmetry would come from precision measurements, perhaps of rates of change of coupling constants, or anomalies in lifetime, or branching ratios, or I should have explicitly said things like the G-2 values. And though we haven't seen supersymmetry, I remain unconcerned, because there are other reasons I believe for why supersymmetry ultimately will be seen. Just before the second scientific run, Physics World in England asked me what I thought about the prospects for this. I told them I was still negative, basically, that I saw no reason to think that the boost by a factor of 2 from the initial 7 TeV in the center of mass to approximately 14 would bring them anywhere close to where I was basically betting that supersymmetry would be where we'd find the scales. And in particular, I alluded to the fact that what we've been doing is like looking for giant sequoias on the east coast of the United States, and then concluding, because we couldn't find them, that they don't exist. Well, the answer to that question is really in this joke. You've probably seen this before. There's a gentleman with lost a quarter, and it's nighttime. He's looking for it. Policeman comes over and says, "Did you drop it here?" He says, "No, I dropped it 2 blocks down the street." "Then why are you looking for it here?" "Because the light is better." And so the expectation of light masses, as I said, I just never found convincing. And as I said, we'll come back to the naturalness argument in a moment. The standard model is extraordinarily successful. In fact, when I give public talks, I like to tell people this is the best tested piece of science that humanity has ever created. On the one hand, we have a theory which makes predictions to better than 1 part in a billion. On the other hand, we have the experimental observations which match those experiments to better than 1 part in a billion. So oftentimes people worry about quantum mechanics or not quantum mechanics, who are not physicists, and I say, well, we know that up to 1 part in a billion, the universe sure seems quantum mechanical. What about superstring theory? That was a disappointment for a lot of people. Well, superstring theory is kind of a strange case in my mind. Although I spent lots of time working on it, there are things about its evolution that I found very peculiar. Some of those things involve its evolution. There was a time when a large part of the string theory communities made statements like, there will be one solution to these equations, it will be our universe. To me, that sounded a lot like Ptolemaic science, Ptolemy, and we're in a special place in the universe. I have very much appreciated Chris's comments about humanity being disabused of its special place in space and time. I would extend that prohibition to think that our universe is in a special place in the equations that we use to study. So 4-dimensional string theory actually exists. Very few people have actually studied it. And the thing that I find most beautiful about it is that it is based exactly on the mathematics of fiber bundles. It has three different sectors. One sector where the currents of space-time properties are described by the string. So in the first line of this equation, you see the symbol x. That string is a four-dimensional string variable, not a 10-dimensional one. There's a different sector that controls the gauge groups. And those are all right-moving, on the surface of the string, these are all right-moving currents. And then finally, the things that look like the family, the replication by family is controlled by a different set of currents, which are actually left-moving currents. And so you can see we have little cartoons at the bottom of this image illustrating these three different classes of currents. Now, this is a part of string theory that, quite frankly, has essentially not been studied to the first level. But it also has certain advantages, which is, to my mind, very important. There's a tautological problem with string theory in higher dimensions. And in fact, it's not just string theory. Any higher dimensional theory of physics has this built-in tautological problem. Shelley Glashow, in the television series program, The Elegant Universe, that was mentioned, actually identified this problem. And the problem is that if you believe that your physics actually starts from some higher dimensional domain, then to get to your physics, you have to specify what we call a compactification technique. And there is none, not to my knowledge, anyone who has ever studied the science of the compactification. So there's a great big hole in the idea of extra dimensions. If, on the other hand, one starts with this four-dimensional view, then at least the starting mathematical points are the same currents that types of currents that you see in the standard model. I'd like to go quickly through the Stern-Gerlach, what I call the Stern-Gerlach legacy, and we know that the Higgs boson spin zero equations are remarkably similar to the motions of excitations on a slinky. We have spin one half particles, which is actually what the famous Stern-Gerlach experiment is all about. Here we have a cartoon illustration of the spin vector of electrons, where some of the electrons are moving vertically in this diagram, and the spin vectors align with the z-axis, either a half h-bar or minus a half h-bar. In electromagnetism, we know that the photon is a spin one object by studying the mathematics of its spin. That leads to the helicity that even non-physicists are aware of, because we all know about polarized glasses. It is also possible to have spin 3/2 particles mathematically. And in the theory of so-called supergravity, we know that it's not just possible, but necessary to have such particles. And so here, again, we see a cartoon illustration of what the spin vector for a graviton moving vertically would be, for an ensemble of spin vectors, how they have to align. And then finally, there's the graviton with the spin 2. I found this illustration on YouTube, which I really like, because what it illustrates is the motion of a linearly polarized graviton wave coming from the back of the tunnel. We're looking down a tunnel here, a circular tunnel, and as the graviton propagates through, it deforms the walls. Now, of course, it's not this dramatic, but you get the idea, and this certainly conveys to the public what we mean when we talk about gravitational radiation. However, gravitational radiation could also be polarized. And so the deformations of the wall, in one sense, look like this. And the deformation of the walls for the opposite polarization would look like this. So, big question. What did the Stern-Gerlach experiment really tell us about our universe? Are group-like structures beyond the Lorentz group and the compact Lie algebra groups relevant to the laws of our universe? And what is the maximal extent of Wigner's observation about the relation of particles to the representation theory in mathematics? For someone like myself, who is a practitioner of formal mathematical theory, these are the questions that, as I think about the progress that's been made over my lifetime, these are the questions that darken my brow and my backward-looking Janus representation. On the other hand, we also can look forward. So what do we see? So it's my belief that these are all the same question, actually, if not closely related questions, and that the only way that we as a species must continue to query nature for the answers to these. I don't have to tell you that Einstein said that Galileo is in fact the father of all science because he drummed it into our heads that beliefs based on nature without observation are basically meaningless. So we must be in constant conversation. So looking forward, what do I see? Well, on the observational side, you folks are going to continue to drive this process. And my claim is that the energy frontier and the precision frontier must be welded together in unprecedented ways for us to continue to meet this challenge. We're going to continue to watch things like the running coupling constants, which we have a little movie here showing the electromagnetic joins first with the strong and finally gravity. As we watch the strength of the coupling constants under the influence of quantum effects at higher and higher energies. We can compare the two, and it was a physicist Kalsikov who pointed out that in the supersymmetric extension of the standard model, it's very likely that there's a single unifying energy where we see the coupling constants of the non-gravitational forces all unify. Here's something that's close to dear to our heart. Those of us who would take quantum field theory remember calculating vacuum polarization for the first time. There's always a cartoon illustration of that calculation. Now, if you take this diagram and tie the two upper ends together so that it forms a V, we get, and then replace the electron line by a muon, then of course what you're looking at is the lowest fundamental, the first quantum correction to the magnetic moment of the muon. And of course, this brings me back to that joyful announcement, at least personally joyful announcement that came out of the G-2 experiment. Because that kind of anomaly is what I was talking about in 2006 as the first herald that we might be on the verge of seeing supersymmetry. Well, this is the standard model as we know it, and the chart that Chris showed is a standard one. It's a standard picture for the standard model. If you pull it apart by according to whether the particle is a carrier of a force versus being affected by the forces on one hand, and then whether they are fermion and boson, you get this picture, and you can see this is not very symmetrical. Supersymmetry simply adds right-left symmetry to this diagram. And oftentimes I've seen standard pictures, the standard model pictures, and talk to the public, because you probably know I talk to the public very often, and people say, that picture looks very symmetrical to me. And then when I show them this, they can get a better sense of why supersymmetry is perhaps something different. I kept referring to the naturalness problem. I like to show this diagram to non-technically inclined people to explain what we mean by naturalness. If you flip a coin, a quarter, and it landed on its edge, and it did this all the time, you would know there's something very unnatural about this. And this is roughly speaking related to the sense of unnaturalness about the need to perturbably correct the quantum corrections to the masses of spin zero particles that we have to finely tune. Now, this is certainly unnatural in the sense that we, to our sense, but I always worried that this argument isn't something that is directly observationally to the extreme measure that so many of my colleagues like Chris and my friend Michael Peston, who I shared an office with for several years as a postdoc, and I have had conversations about. There's also this observation about if you look at the masses of the top of the bottom quark, the mass of the Higgs and the top quark, and think about stability, that it looks like we may be living in a metastable phase of this diagram. We know that the universe vacuum has fluctuations, and if you're in a metastable phase, then you have to worry about, is there a true vacuum somewhere close by? And by the way, that's sort of the reason I really think supersymmetry is around, folks. I think it's about vacuum stability, not the things that are mostly cited. So On the formal side, what can we do to join your drive for precision and energy? Well, first of all, I think there are going to be, there are already signs of new tools being developed by those of us on the formal side. Algebraic topology, well, what does that mean? Well, that really is cluster algebras. It's the so-called amplitude hedron that you've heard a lot about, that Nima Arkani Hamid has spoken about, and the associative hedron. All of those things are elements in algebraic topology. So there are lots and lots of signs that algebraic topology for the formal theorists is a way to usefully think about adding to the possibilities of talking to our experimental colleagues. I think Chris was alluding to this when he mentioned higher order gluon calculation, Feynman calculations, because there's a whole machinery that's coming out of algebraic topology about what those scattering amplitudes look like. Graph theory seems to be very important in this new world. And I have to remind you, it was actually hiding when we did the work on SU3, because I showed you those representations, but those representations are actually polytopes. And so graph theory is a generalization of polytopes. And I have, in my own research, uncovered some evidence that supersymmetry is a more robust kind of graph than we encounter in compact Lie groups. Information theory seems like it plays a role. You've probably seen a lot of work on information theory and the structure of space-time. But again, I've been engaged in research for about a decade where we found some very strange signs of information theory inside of the representation theory of supersymmetry that I am currently attempting to build. Computer-aided conceptualization. Well, a lot of people talk about machine learning, and one of the really interesting questions that has occurred is, as you look very carefully at machine learning, is it a model for physics? In fact, does it look more like perhaps some of the physics that we do than simply modeling physics? And then finally, the possibility exists that perhaps evolutionary theory itself will become one of these tools. We know that there's a race on to build quantum computers, and that means that we as a community will likely be using these devices to assist in our calculations. And I also like to tell people that learn how to use this technology, because it's like putting on the Iron Man version. It's like putting on the mathematical version of the Iron Man suit. Let me go and close now. I'm currently studying a very strange object. It's called the hexapenta Runcie truncated 7 simplex. It's a diagram that has 40,000 vertices and over 100,000 edges. And you might wonder why a physicist is studying such a thing. Well, it turns out that we have some evidence that supersymmetry is related to this very peculiar mathematical object. That's the thing that I was showing you at the beginning of this talk. It wasn't just a ball of confusion, it's an actual mathematical object. And it's a generalization of this object, which is it's the simplest mathematical permutahedron. And we can show that just like those quark representations map to different nodes on those lattices that I showed you, we've actually completed work already that shows that different supersymmetric multiplets actually map to this thing in the same sort of way. And finally, we've used this kind of approach to answer some questions that have never been answered in the context of supersymmetry. These things are, again, polytopes. This particular one has to do with M theory, the so-called limit of 11-dimensional M theory, supergravity, 11-dimensional limit of M theory. And we've used this to unravel a system with over 2,147,483,648 boson degrees of freedoms and fermion degrees of freedom. And so these new tools, I am convinced that formal theorists will be applying them. And if you can force some of us to think about some questions, thank you very much. I'd like to acknowledge, provide acknowledgements for the use of some of my CGI units, as well as their creator. Thank you, and I'll take questions.
Thank you so much for joining us and for giving us this wonderful talk. I believe Tejinder had comments to add, and then we can field any other questions and move on to a discussion section. So Tejinder.
Yeah, thank you. Thank you, Jim. That's a very fine overview. I really enjoyed listening to you. I had a comment regarding the extra dimensions. It's not really necessary to assume that the extra dimensions are real. They can be complex. Only classical systems have to live in a real valued 4-dimensional space-time. Quantum systems can live in a complex valued higher dimensional space-time even at low energies. And in a group like E6, where the subgroups like spin 10 occur, the symmetries of the extra dimensions are actually the symmetries of the standard model, like the fiber bundle that you showed. I'm saying it's actually unified with the 4-dimensional base in spin 10, and only classical systems need to come down to 4D. And I don't compactify, I never compactify the extra dimensions.
May I respond?
Yeah, please, I'll be grateful.
So as I said, there is actually a philosophical problem, tautological problem with the concept. It's much deeper than just saying they can. You see, one thing about the standard model, which is often overlooked, is that it's complete in a philosophical sense. What do I mean by that? Well, the standard model, what are our inputs? Well, they're the gauge groups and they're the representations that are present. And we have complete control over specifying those things. We can specify the gauge groups, we can specify the representation content. And that means that in principle, not that anyone would ever do it, but in principle, we can write down every possible description of our universe that's based on the gauge theory. This is where the problem with higher dimensions breaks down. You see, it's not about a particular theory, it's about the tautological completeness of the idea. Namely, can you write all possible theories? And you can't.
I think your description is incomplete because you have 26 parameters and you do not know where they came from. Whereas when I invoke higher dimensions, the algebra of the full 10 dimensions is actually fixing these 26 parameters for me. At least 10 I have been able to fix it so far. So
Yes,
there's a merit to higher. Please go on.
But you see, one of the, as I said, because I started out as a phenomenologist, I actually believe nature's supposed to tell us the answer to those kinds of questions. I'm happy to continue this kind of discussion by email, but if there are other people who would like to ask questions, I'd like to get to.
Thank you. I'll write to you. Thank you.
Thank you so much.
Thank you.
Yeah, in the interest of time, I'd like to facilitate a discussion between both speakers that I think really across both of your talks, one of the main consistencies is that the future of our field is going to really outlook to precision measurements. And I was wondering if you could both comment on and discuss the next horizon for these precision measurements and where you see this moving.
I will defer to Chris to start, but I'm happy to weigh in.
Yes. So I would not say that the future is solely in precision experiments. I think precision is very important. Historically, it has been important. It gives us indications of things that we don't understand, or sometimes confirms ideas that we put forward tentatively. But in this case, I would agree with Jim's formulation that the union, a conversation between search and discovery on the one hand and precision on the other hand is very important. And I would say again that paying attention to developments in other fields is very important. For me, there are, as rich and wonderful as our experiments have been, there are many places we haven't looked, even among those that are accessible to us. And we don't know what we're not going to find. So I'm a believer in a very broad set of investigations and with attention and conversation among them. Pretty unsatisfied answer, right?
Well, no. Look, you didn't say anything that I find disagreeable, Chris, because you'll notice that I said it would be the two would be welded together in unprecedented ways. I think that's the way forward. And so if one is on either of those two arms separately, I think we lose out on the possibility of actually making great discoveries and increasing the rate of our progress of our science.
So on that note, really quick, if I can just jump in, what do you each feel is, especially in this last week of us advocating for our own individual projects through the Snowmass process, what do you think is the best encapsulation of that idea, of this broad support that we need to seek through the funding agencies, through the P5? What do you think is the best defense of that, other than, as Chris said, we don't know what we won't find? Is there a better way of maybe telling that to the funding agencies that say, we think that there are good ideas here, there are maybe controversial ideas, but still ones that are worth pursuing?
I assume, are you asking Chris or are you asking me?
Both.
Oh, okay.
You're the head of the APS, so hopefully I can.
No. No, I am not the head of the APS. My presidency ended the 1st of this year.
Congratulations on your tenure.
No, you should say congratulations about surviving a year of incarceration.
Well, we were glad that you had that. But
telling the story, no, that's a very good. I need a second to think about that. No one's ever asked me. Look, I was on the so-called board of overseers when it was clear that the precision frontier would be a major effort at Fermilab, and I was a big supporter of that because basically because that's what I said in 2006. I even before other people were talking about it, I'm like, this is where I think the future lies. So I've been consistent in my career about the precision frontier. But in order to tell the story to the agencies in a way that's compelling, the things that make me passionate about the precision frontier are things that I don't yet know how to even talk to the public about. So much less the agencies. That's a hard question. I'll give it some thought now that you've put it to me.
Thank you.
So again, I would say that it's so hard to separate these things. What, in my experience, the agencies listen to are serious proposals with the possibility of rich science brought forward by serious people who have both a gleam in their eyes about new things to do and a track record, whether as individuals or as teams or as tradition of the field, for delivering good science in response to the support of our funding agencies. Just to give another example of a place that is hard to separate precision and energy. So the first step in the FCC would be an electron-positron collider in a big tunnel. That's part of the feature of that. And one aspect of it is to do Higgs physics in a precision way, so fine enough. It also wants to go a little higher in energy, and then it carries on with the proton-proton machine that would go much higher in energy. But a feature of that, if it can be done, is to have the running on the Z peak, Z boson peak, in which you would accumulate 10 to the 12 Z bosons per year, giving a new window on flavor physics that we haven't seen before. So, part of the appeal of that project, for all its big price tag and long time scale, is that it would enable so many different things to be done. And I think that's often the case for, if you think about the current colliders, even going back to the Tevatron, the W boson had been discovered before. The Tevatron made many more W bosons than had ever been seen before. LEP made measurements in a different way. The LAC makes measurements even better in the way that the Tevatron first pioneered. So I think a lot of these things are tied together. And there are things like neutrino-less double beta decay that are not instrumentally tied to most of the other things we're doing, maybe to dark matter searches, but which have a very intimate intellectual connection to everything else we're doing, and which have the capacity to change the way we think about the world. So I guess I'm a partisan of a broad approach to things.
So, I think that question came from Josh to me about making the compelling case. And let me just say that because I've always thought that supersymmetry was going to be hard to find, that really is for me the driver. But given that the agencies have been burned because our community was so overwhelmingly, and one could say hysterically engaged in the idea that we'd see light supersymmetry, that anyone doing funding is not going to take that as a good argument about moving forward with projects. So you've really given me quite a conundrum, Josh, about thinking about precision in another way.
We did receive another question on the form. It's, how do you think the community should handle these long timescales between gigantic experiments? For either of you.
I would generalize the question. I think that's a very important question. It applies not only to experimental physicists, but in particular to people engaged in accelerator technology. Especially because not all of these projects will actually be realized. And so it's very important that we as a field create a reasonable career path for people who do the things that we can't exist without. I don't have an answer for that except to call attention to it. I wrote a little bit about that in an article called Dream Machines a couple of years ago. But I think, you know, taking care of our young and middle-aged and elderly is extremely important. Often it's a little easier for experimenters because you can participate in experiments at different stages and at different scales than it is for accelerator builders who are almost necessarily locked to a single enterprise at a given moment. But in both cases, we need to be very thoughtful about how we create and sustain opportunities. If I just add a little remark, Jim has spent more time around deans than I have, but university deans believe that they have very sensitive receptors, and at the slightest hint that a field is not going to receive funding or receive adequate funding, they will amplify that signal and or noise and make decisions about hiring people into their departments. And it is incumbent on those of us who have superior wisdom to help them understand the truth and to create positions in fields that have great promise.
So you're right about deans, Chris, but it works in with both phases, right? I mean, they also, what you're basically describing is a herd effect that I've seen a lot in universities in my I'm now in my 51st consecutive year teaching. So I've seen this quite often, and I don't know how to counteract the impact that occurs in the thinking of a dean's mind when they reach this point. It's something that a professional organization like the APS really needs to work on with regard to speaking to the agencies and making sure that this doesn't happen, to essentially enunciate for the agencies the resources that they then put at risk by prematurely shutting down a particular line of research. So within the university itself, I've never seen a way to counteract that effect unless you have wealthy donors who are who are committed to a particular line of research and will open their purse strings. That's the only pushback I've ever seen work.
I just maybe to comment back on that really quickly, and then maybe we can close. But from what each of you have said here, I think that this maybe affects our theory colleagues the most in some respect, this sensitivity. So I guess one thing maybe to put out there from each of you is, is there a semi-ideal collection of specialities that you think a top tier R1 institution should absolutely maintain as far as different professors in order to keep that broad general knowledge going through these potentially very long experimental phases upcoming? So for instance, I mean, like,
go
ahead.
I have an opinion about that, which is that it's a mistake to hire people who can only do one thing for the rest of their lives. You want to have people who will be able to move as fashions change, and ideally to have people who will help others understand the right things to think about and the right way to think about them. In building a group, it's very important that you have a diversity of contemporary interests among your faculty members, but that there be a core. Because if you only hire people who are doing things on the fringes, they may find it difficult to communicate with each other. Whereas if you have a core, that can be the tree trunk that enables everybody to communicate with everything else. There are all sorts of things that people can do wrong and that are not so challenging, but a little bit challenging to do right. But having a group of people who are nimble, interested in a lot of things, speak to each other, gain stimulation from experiment, and especially in a university setting from mathematicians and people in other departments, is extremely healthy. When I was young, of course, I gave lots of advice to old people, which is a privilege of the young. I feel less comfortable as an old person giving advice to young people now because I was always brash, I guess. But I think this is the way that you go about it, to have people, try to hire people who are going to grow for many decades. And that's true in theory and experiment and everything else.
So I just have one codicil to that, Chris. I would say that, yes, I want people who can maneuver and basically surf the changing currents that are out there, because that's, if you're going to have a career, several decades long, the currents are not going to be the same at the end that they were at the beginning. That's completely clear. So yes, I would say, yes, I want to find people who can figure out how to maneuver those currents. But part of, for me, maneuvering those currents is also keeping a keen focus on possible long-term questions that each individual can work while surfing those currents. Because that's what I think is a very important thing, because not everything is going to be answered within a decade or 2 decades. There are questions you can ask, like this problem that I talked about solving. That question had been around since the late 80s. Nobody knew how to solve it. And as far as I can tell, I'm the only person in the world who knows how to solve it. Now, you could say, well, maybe it wasn't important. Well, maybe it wasn't, but maybe it was. We can't judge the future. So yes, I want people flexible. I also want people who have an internal sense of what are wicked questions, I guess is one way to say it.
Okay, and with that, we're a little over time, but I want to really thank again Jim and Chris for coming to speak with us and joining us here. We very much appreciate your contributions to this colloquium series, and thank you to everyone who attended and submitted questions. we'll see you at the next installment on April 1st. Thank you so much.
Thank you.
Thanks.
Thank you, Cal.
Bye, everyone.